Hello everyone, so today's video is going to be about the transformation equation and how it is used to transform parent functions. This video is going to cover what each part of the transformation equation does to a function, what is a parent function, how to write the equation for a transformed parent function, and lastly how to graph these transformed functions. So, what do these transformations do? Well, if you look at the graph, I made a rough sketch of a function to demonstrate this. Starting with the negative sign that precedes the a, when a function in its transformed form has a negative sign there, it means it's been reflected in the x-axis. This is illustrated by the red graph. Next, we have a reflection in the y-axis. This happens when there is a negative sign in front of the b value. A, depending on its value, can be a vertical stretch or compression. When a, ignoring the negative sign if it's there, is greater than 1, you'll have a vertical stretch. So you can imagine the original function being pulled upwards in the vertical direction, producing the function illustrated in red. When a is a value between 0 and 1, also ignoring the negative sign in front of the a, if there is one, then you'll see a vertical compression. So you can imagine the original function being pushed down in the vertical direction, producing the function in red. One thing I want to point out, something I often see the students I tutor confused with, is that when they see a fraction or a number with a decimal, they automatically assume that it's a compression and that the value is between 0 and 1. Although numbers between 0 and 1 are always fractions and decimal numbers, not all fraction and decimal numbers are between 0 and 1, so it's not safe to assume this. Next, we have a horizontal stretch. So ignoring the sign in front of the b, if b is between 0 and 1, you're going to have a horizontal stretch by a factor of 1 over b. You can imagine the function being stretched outwards in the horizontal direction, producing the red function. Notice how whenever you have a stretch, it's always by a factor that is greater than 1. Next, we have a horizontal compression. Once again, ignore the negative sign in front of the b if there is one. If b is greater than 1, you'll see a horizontal compression by a factor of 1 over b. You can imagine the function being pushed inwards in the horizontal direction, producing the red function. Notice how whenever you have a compression, horizontal or vertical, it's always by a factor that is between 0 and 1. Now we're going to talk about horizontal translations. So when the sign in front of c is positive, the function will translate c units to the left. And when the sign in front of c is negative, the function will translate c units to the right. For vertical translations, if d is positive, your function will move up. If it is negative, your function will move down. Now let's talk about parent functions. Parent functions are the most simple version of a given function, the most simple version of a quadratic, cubic, quartic function, or of a reciprocal or square root function, or the most simple version of a certain trig function, like sine for example. Those are all examples of parent functions, and I've also written some on the screen. I'm going to go over a few examples of how to use the transformation equation to transform these parent functions. Let's start with f at x equals x squared. See how in the transformation equation you have a part that says f at negative b times x minus c, the section that is highlighted. This is what you have to figure out for every parent function, and once you know what it is for the parent function, you can plug it back into the transformation equation to get the transformed version of that parent function. So if f at x equals x squared, then f at negative b times x minus c would be negative b x minus c squared. So instead of plugging in x, you're plugging in negative b times x minus c. And now that we know what this is for this parent function, we can plug it back into the transformation equation. So essentially, it's replacing that highlighted section. And you get this. So now anytime you see a quadratic function in this form, you'll know which transformations are being applied to it. Or if you're asked to write the equation for a quadratic that's been reflected over the x-axis, translated 3 units to the right, etc., you'll know how to do it. Now let's try it with the reciprocal function. So if f at x equals 1 over x, then f at negative b times x minus c would be 1 over negative b times x minus c. So plugging that back into the transformation equation where the highlighted section is would give us negative a over negative b times x minus c plus d. Since a is being multiplied by 1 over negative b times x minus c, it ends up on top in the numerator. Let's do another one with the square root function. So if f at x equals square root of x, then f at negative b x minus c would be the square root of negative b times x minus c. So the transformed equation would be negative a times the square root of negative b times x minus c plus d. Now let's do one more example with the sine function. If f at x equals sine x, then f at negative b times x minus c would be sine of negative b x minus c. So plugging that back in would give us negative a times sine of negative b times x minus c plus d. Hopefully now you get the gist of what we're doing and are able to apply this to other parent functions. So now I'm going to go into how to use these transformed equations for graphing. Functions are made up of a series of points called coordinates. Each coordinate has an x and a y value. When you transform a function, you're transforming all the points in that function. So one way you can graph a transformed function is by transforming some of the coordinates of their parent function and graphing those. In my chart, I have x1, y1 as one coordinate of my parent function, x2, y2 as another, so on and so forth. And then I show how I transform both the x and y portion of each coordinate. The factors along with their signs for the stretches or compressions are multiplied by x or y, and then the translation is added. For horizontal transformations, b keeps its sign and its reciprocal is used. C changes its sign, becomes positive if negative in the equation, vice versa. For vertical transformations, A and D remain the same and keep their signs. I know this looks a bit intimidating right now, but it's way easier in practice, so let's do a few examples. Example 1 says, write the equation of the function whose parent function is f at x equals x squared, and went through the following transformations. Then graph this function. So since we're transforming the parent function of a quadratic, we need to use this transformation equation. Remember we talked about earlier how to get this equation. I want you to think about what this equation will look like for a bit before I give you the answer. So pause the video for a second and see if you can figure it out. Okay, now I'm going to go over the answer. If we have a reflection in the x-axis, the a value will be negative. We have a vertical stretch by a factor of 2, and since a is our vertical stretch, it will be 2. Since there is no reflection in the y-axis, there is no negative sign in front of the b value. We have a horizontal compression by a factor of 1/3, but remember the factor for a horizontal stretch or compression is always the reciprocal of the b value in the transformed equation. So you have to remember to flip that factor before you put it back into the equation. That's why it's 3 and not 1/3. We have a horizontal shift 2 units to the left. Left is into the negative direction, so the sign needs to be positive. Remember the stuff with regards to the horizontal transformations is a bit opposite of what you'd think. And finally, you have a vertical translation 5 units up, so that would be +5. Now let's go over how to graph this function. I'm going to choose some good points for my parent function, some points around the origin. These are going to be the points I'm going to transform. The things that affect my x are the horizontal compression by a factor of 1/3 and the horizontal translation 2 units to the left. So I'm going to multiply x by my factor and translate it 2 units to the left in the negative direction. The things that affect my y are the reflection in the x-axis, because if you think about it, it's the y value of the coordinate that's changing. So for example, if we have this coordinate 2, 2, and we reflect it over the x-axis, is going to become 2, negative 2. So if we go from 2, 2 to 2, negative 2, that x value right here stays the same. It's that y value that's changing. So that's why a reflection in the x-axis changes your y value or affects your y value. Anyways, other things affecting my y are the vertical stretch by a factor of 2 and the vertical translation 5 units up. So I'm going to multiply my y by negative 2 for the reflection and the stretch, and I'm going to be adding 5 for the vertical translation. Now that we have this, we're ready to transform our parent function coordinates. If we look at our first coordinate, negative 2, 4, we can see that it has an x value of negative 2 and a y value of 4. So to transform this coordinate, we have to apply the horizontal transformations to our x and our vertical transformations to our y. 1/3 times negative 2 is negative 2/3. Minus 2 is negative 2 2/3. Negative 2 times 4 is negative 8, plus 5 is negative 3, and that is how you get your new transformed point. When you do this enough times, you get to see the coordinates of your transformed function. So this is the graph of f at x equals negative 2, 3x plus 2 squared plus 5. Let's try this again with another example. Example 2 says, write the equation of the function whose parent function is f at x equals sine x, and went through the following transformations. Then graph this function. Since we're transforming the parent function of f at x equals sine x, we need to use this transformation equation. Pause the video for a bit and see if you can figure it out. Okay, now I'm going to go over the answer. There is no reflection over the x-axis, so there is no negative sign in front of the a value. There is a vertical compression by a factor of 1/2, so a is going to be 1/2. There is no reflection over the y-axis, so there is no negative sign there. And there is no horizontal stretch or compression, so there is no b value. There is a horizontal shift 90 degrees to the right, into the positive direction. So we have to do the opposite of what you'd normally think and use a negative sign. And lastly, there is a vertical translation 1 unit up, so d is positive 1. So what's affecting my x is the horizontal shift 90 degrees to the right, into the positive direction. So I'm going to write plus 90 degrees. My y is being affected by the vertical compression by a factor of 1/2. So I'm going to multiply y by 1/2. It's also being affected by the vertical translation 1 unit up. So I'm going to add 1. Now to graph this function, I'm going to take some good points from the parent function, f at x equals sine x, and transform those. So the coordinates in red and the graph in red are my transformed function, f at x equals 0.5 sine x minus 90 degrees plus 1. Thanks for watching.